Okay, thank you very much. So welcome everybody to the seminars of the IAG-USP. I like to take the opportunity that Reynaldo and Vicky, the organizers, left me to introduce our guest today, which is Coleman Miller. Cole is one of the guys who's heavily involved in something we dreamed when we were kids, that is to measure neutron stars, which are point-like and very small, and then at that time you could, publish thousands of papers essentially wrong because you have no data. But now this has changed, and Cole will talk to us about how he managed with the large team of people to get into the measurements of that wonderful object. The Cole is a product of the Berkeley University, has been in Maryland since 30-something years, doing essentially the same, which is trying very hard to understand compact objects and phenomena around them, like accretion and many other things. And then I hope that you enjoy his seminar about the latest real true developments in compact star physics. Please go. Thank you very much for your presence, and that's up to you.
Right.
Excuse me, Professor Coleman, just a little announce before you start. The questions today can be done during the presentation, so anyone who has a question, just open your microphone and ask the question directly to Professor Coleman. And for those who are following and in YouTube, the seminar, you can also, during the presentation, write your questions and we will, in the chat, and we will bring it to Professor Coleman during the presentation. Thank you. Please, Professor.
Thank you very much, both of you. I appreciate the invitation, and indeed, I do look forward to any questions or comments that you have during the presentation so that we can be much more interactive and you can get questions off of your mind. I am indeed going to talk about learning about neutron stars with NASA's NICER mission. NICER stands for Neutron Star Interior Composition Explorer. The extra R because this is the way that NASA names things, but it works. And what I'm showing here on the front, on the left, you have the NICER telescope itself, which is on the International Space Station. And on the right, you have some of the people who are constructing the detectors. And I do this to remind myself that enthusiastic though we may be about whatever we're learning from the data, we owe a profound debt of gratitude to the tireless work of the people who constructed the instrument that has worked so well. My talk is going to be relatively simple, and I'm going to tell you first about our results and how we got them for two pulsars, which have been observed and analyzed with NICER. The first one has been published. The second one we're hoping to post within the next few days on the archive. And then I'm going to talk about the implications of this work for the equation of state of the matter and neutron star cores. This is the pressure as a function of energy density, and it lies at the heart of things like mass versus radius, maximum mass, things that you could measure with gravitational waves, such as how easily deformed a star can be by a tidal field. Now, I'm going to focus entirely on the work by my team within NICER. There are two teams that work independently. Miller et al., those are the ones that we have, and the work by Tom Riley and his colleagues, and Gert Rijmakers and his colleagues. I definitely encourage you to look at those, but I will focus only on my work. I don't like it when people try to hold off the results until the last second, so I'm just going to give you the main results first, and then I will go back to give you more context. This is for the people who are able to look at this and say, oh, okay, this is what it means. Two pulsars have now been studied extensively with NICER. Other pulsars have been measured, of course, and examined, but these are the ones where we're fairly confident of the results. The first one, this J0030, spins at about 200 times per second. So this is a millisecond pulsar, and it's really moving around very nicely. The second one, J0740, spins more rapidly. In fact, that one spins roughly as fast as your kitchen blender. For the first pulsar, where we reported the results in 2019, this is an isolated pulsar. It does not have a stellar companion. And that means that we cannot use any of the many techniques available for binaries to get an independent measurement of the mass. It was therefore necessary to analyze this without that knowledge, and we obtained a radius of about 13 kilometers with a 1 standard deviation uncertainty of about 1 kilometer and a mass of around 1.4 solar masses. But with the second one, even though, as it turns out, this is much, much fainter than the first, the X-ray flux in the nicer band is about 20 times lower for J0740 than it is for J0030. But the reason that we studied it is it has a high mass. The mass of about 2.08 solar masses is the highest precisely and confidently identified mass for any neutron star. And as a result, the study of this heavy pulsar gives us extra information. And therefore, although when you look at that radius, you might say, wow, that's a very uncertain radius, it still has quite important implications for our understanding of the dense matter in neutron star cores. And just to set things up for later, our philosophy here is that when we are analyzing the data from NICER, which is an X-ray instrument, we allow the radius to be any value that fits the data. We do not impose our prejudices about the size of the star that it should be. When we later use our measurement in order to understand more about the pressure versus energy density, that is to say, the equation of state, then we do incorporate other information from nuclear theory, from gravitational wave measurements, and so on. This is a philosophy that we have applied. Okay, but now let me kind of backtrack and give you the question, why should we study neutron stars? The obvious and correct answer is because neutron stars are awesome. They are incredible extreme physics factories. They have the strongest magnetic fields in the universe. They have superconducting superfluids with transition temperatures of at least 100 million degrees Kelvin. They have all sorts of strange condensed matter features, like the so-called pasta-antipasta sequence in their crust. And the giant question mark in the center is what we're focusing on today. This is their cores. The thing is that the cores of neutron stars are at several times nuclear density, and they are, in a technical sense, cold. What this means for the interested is that their temperatures are much lower than their Fermi temperatures, meaning that the temperature has almost no impact on the structure. Because of these features, and because these are very neutron-rich, you cannot study this state of matter in laboratories. We don't know what it is. The composition is something that people argue about fiercely in the nuclear community. Is it mainly nucleons, meaning is it mostly neutrons with a few protons, electrons, muons? Is it strange matter? So are the baryons, or the 3 quark bags, are these things that have strange quarks in them? It's been speculated this might be true. Is it quark matter, so that instead of having quarks bound up in 3 quark bundles, instead you have free quarks, as you would expect at very high density? Are these condensates, meaning Bose-Einstein condensates, but instead of using atoms, these would be things like kaons? There's extreme exotica about this. And because we cannot probe this state of matter in the laboratory, there is a lot of argument in the nuclear physics community about what this could be. And we have the possibility, if we can do proper measurements of neutron stars, of their mass, of their radius, and so on, to get insight about this. And in particular, radii are very important. The figure that I am showing on the right gives you an indication of why. This is already a decade old from a paper which revealed the first neutron star with a mass close to 2 times the mass of the sun. And what you're looking at here on the vertical axis is the mass, more technically the gravitational mass, in units of a solar mass. And on the horizontal axis, you have the circumferential radius in kilometers. And the point here with the red bar, this J1614, this is the one that had the high mass. The curves show the mass versus radius relation predicted for a variety of candidate equations of state. And as you can see, all of them have some maximum mass that they can reach. That's where it kind of curves over. But obviously, if you can't reach the mass of the highest mass neutron star, your equation of state cannot be real, cannot be correct. Even though we have a lot of the curves here that can reach that 2 solar masses, what you can see is that when you look at this range of radii for all of these equations of state that can manage to reach this high mass, there's a huge range. So what this tells us is that it would be absolutely great if we could measure radii. But there's a big problem with this. The problem is, I guess I can phrase it in the following way. If you think about how you might measure the mass of a neutron star, you're certainly not guaranteed that you can do it, but if you have a neutron star in a binary system, especially if the other object is also a neutron star, there are many things you can do looking at pulsations from a pulsar, for example, to get you a good idea of the mass. This is because all you need are Kepler's laws, and mass has an effect at a distance because of its gravity. But now we think about how we could measure the radius. Well, the radius doesn't have an effect at a distance. So if we think about it, maybe the first thing that comes to mind is how we measure the radii of stars. The stars are really far away, they're points. You can't say, I know the distance and I know their angular size and therefore I know the radius. That won't work. But what you can do is you can say, I'm going to pretend that the star emits like a black body. I figure out the distance with parallax maybe, and from that distance, from the energy flux, and from the temperature that I measure, so I can figure out which black body it is, you just apply the black body formula and you have the radius. Not only that, if you check, then a number of cases where you know the answer, like our sun, or any of the stars where Kepler, the mission, astroseismology has given us an independent measure, and we find that for a lot of stars, our approach works really well. Filled with confidence, you therefore do the same thing with neutron stars, and you get ridiculous answers. 2-kilometer radius, 5-kilometer radius. No, it's at least 10. And it turns out that this is a big problem. It's a big problem because it looks like you've got a great fit to your spectrum. You just apply a black body. It's in the X-rays, but it's a black body. You put your black body down on top of the data and it fits. Outstanding. You're in great shape. The problem, though, is that it's not a black body. It has the shape of a black body, but it's not a 100% efficient emitter, which is another thing required for a black body. So this means that you have potentially huge systematic error. And the especially damaging aspect of this is that you can get a fit that really looks good. Statistically, it looks excellent, but you can be very biased. Now, let me give you an example of this. This is something I generated because before the nicer work, when people used X-ray observations to get neutron star radii, they typically would look at the luminosity from the object and look at the spectrum, just like we did for the stars. And they know it's not actually a black body, so they use something else, but even then they can be badly fooled. Here's an example that I constructed. What we're doing here is we're imagining that we have a star with a temperature that varies over the surface. At the equator, KT is 2 kiloelectron volts, and at the pole, It's 0.2, so it's a factor of 10 difference. But we are imagining, with this data that we have constructed, that we're going to fit this with a single temperature black body. You might think this is going to be terrible. Just an awful fit, because after all, it's a factor of 10 variation in temperature. But in fact, no. This is the chi-square per degree of freedom, 180.8 out of 173. That's fine. That's a good fit. So it looks like you've got an excellent fit. Now, when you actually do the analysis, the real radius I put in is 12 kilometers. When you fit, here's what you get. It's 13% low, but the main problem is you're off by 10 standard deviations. So the difficulty is that you can get an apparently good fit. You can get an apparently very precise answer about the radius, but you can be tremendously biased. This is where the extra information available with NICER comes in a critical way. You see, NICER is not just figuring out the energy flux and the spectrum. It also has tremendous timing capability. It can time individual X-ray photons to 100 nanoseconds or better. This means that as you accumulate data on an individual pulsar, it is possible to not only figure out the spectrum and flux, but also the spectrum as a function of the rotational phase. This is an extra dimension of data, and extensive work over a number of years by my collaborator Fred Lamb and myself, and others as well, has shown that you do not have this deadly combination where you can have an apparently good fit and yet be very biased. We've done this with synthetic data. We've taken all sorts of deviations from our standard model, oval spots, spots with a temperature gradient over it, and so on. And we find, however, that if it's a good fit, it's a reliable measurement of the radius. And this is what has given us confidence about the results we have with NICER. Are there any questions at this stage that I can answer, or should I continue? Okay.
Go ahead.
Go ahead. All right. The general idea that we have for NICER is that we're using Bayesian statistics, and we imagine, as we have here, that we have a star. This is maybe one side, another side, and there are different regions on the surface that are hotter than the cooler background. These we're just calling spots or hot spots. So we imagine that we set up a star of a given radius, a given mass, with spots at certain angles, and then we construct the energy-dependent waveform, therefore including both spectral information and rotational phase information, and we fit it using our Bayesian techniques. This is something, obviously, that we've had to test extensively. This is a partial list. As with anything, I'd be happy to go into more detail if you wish. We have compared our codes with others within the NICER team. We have done a lot of analysis of synthetic data, which is critical because if you know the answer, then the answer you get can be compared with that. And it passes posterior predictive assessment tests, which is to say that when you look at a fit to real data, you can say, well, how good is that fit? And in some ways you can use a chi-square, but in other cases you can say, well, let's suppose my model were actually correct. Would the data I see be an expected draw from my model? And it passes all of these tests.
Excuse me?
Yes.
Please, just a clarification. When you say rotational phase, you mean the profile of rotation latitudes of the star?
Yes, exactly. So.
Okay, thanks.
Right. And in case you're wondering, by the way, both of the objects we're examining are pulsars as seen with radio waves. And therefore, it has been possible to have very precise timing. And so we do know the rotational phase to high precision. Thanks for asking.
Thanks.
For our first neutron star, J0030, we had a couple of fits, both involving oval spots. And On the left, we have one example of an equal area projection. This is the type of thing you might see in the cosmic microwave background. And the right, in each case, we have a projection we would see from the south rotational pole, where south is defined as the rotational hemisphere opposite us. So by definition, we are in the north hemisphere. And looking at this, something that is odd is that this does not resemble what you might see in a textbook. In a textbook, magnetic fields always seem to be centered dipoles. Here we have 2 or possibly 3 spots, and they are ovals instead of circles, and so on. And this is something that actually caused some people to believe that our results were incorrect. However, I will point out that the idea that magnetic fields should be centered dipoles, meaning dipoles centered on the center of the object, this is not necessarily true. Here we have Uranus and Neptune. And no, they're not centered on the center of the star. They're offset by some strange amount. And the pulsars we are looking at go through a complex evolution. It's thought they at least had a companion at one time. Matter flowed from the companion, spun the star up and down, and anyway, there's no reason on Earth that this should be simple. It reminds me of a story from a conference in the 1950s, which was about stars. And as people were talking about all the different complicated things that existed in their studies, some member of the audience said, well, I'm really surprised that we cannot understand such a thing that is as simple as a star. And Fred Hoyle, the great astrophysicist, said, well, you'd look simple too at a distance of 10 parsecs. So I think what this shows is that when we look carefully at something, it's not so simple anymore. As I indicated, for this first NICER pulsar, we have 2 models, one with 2 ovals, one with 3 ovals. And this is just showing you that when you look at the posterior, meaning the final probability distribution, 2-dimensional in mass and radius, then you end up with basically the same answers for both. So it's not like these are radically different from each other. And this is good because it suggests that we're not running into a problem where the model we have chosen to use gives us a radically different answer from a model that we maybe didn't use. One other thing is that this actually does fit the data well. What I'm showing you here looks like a test pattern from a television, and there are no obvious patterns, and that is a good thing. Horizontally, we have the rotational phase bin. We divide the rotational period into 32 bins, and vertically on the left, you see that we have the energy channel numbered by NICER. Basically, if you multiply this by 0.01, you get the energy in keV. So this goes from about 0.4 keV to a little more than 2 keV. And on the right, the bar is chi. So this is the signed square root of chi square. There's no pattern. There's no obvious residual. The overall chi-square is good. So all of this suggests that we do, in fact, have a good fit. And based on our previous studies, this gives us some confidence that our model is, in fact, accurate and the answers that we get are reliable. Anything else at this stage? In that case, let me move forward to talking about the second pulsar. Now, the results are not out in detail yet, but about 4 weeks ago, one of the members of the other team and I both gave presentations at the American Physical Society April meeting, where we gave some of our initial results, and that's what I'm showing you here. And something that I'll mention in a little bit more detail going on here is that I mentioned earlier that this is a very weak source, 20 times weaker than the previous one. We therefore are not able to use just one set of data. Not only do we use the NICER X-ray observations, we also use the XMM Newton X-ray observations. This is run by the European Space Agency. And we use information from radio telescopes that can give us the mass. What I'm showing here in the corner plot is the two-dimensional posterior and then the individuals for the radius and the mass. For the mass, you see the dashed line. That's what we got from radio. The gray histogram is what we get after all of our analysis. So you can see we really needed that radio information. The X-ray does not tell you much. And the radius is given there on the right. So it's roughly 12 to 16 kilometers at 1 standard deviation. Now, before discussing some of the details here, I will mention that it may seem that this is a very uncertain result. But the important thing is that this is a heavy pulsar. As I mentioned, it is the heaviest neutron star that we know with some precision and reliability. And therefore, any measurement of the radius is important. In particular, there are some models which, even given the measurement we had of J0030, would have predicted a significantly smaller radius. You may recall from the plot that I showed of different mass-radius relationships that when these individual equations of state get near their maximum mass, they kind of bend over and go towards a smaller radius. So there are plenty of models suggesting that the radius might be 10 kilometers. Therefore, this is an important result. Now, this is an outline for our method, and I'm going to give you some details about this. If you want, I also have a number of backup slides where I will be happy to go over additional aspects of our approach. This, as I indicated, required that we incorporate data from many different sources, and therefore, just from the standpoint of the analysis, it posed different challenges than the first pulsar. I will tell you a little bit about our modeling of the hot spots, our approach to this. I will tell you about the roles of each of the different parts of the data in our final answer for the radius. I won't give you details, although I could if you wish, about the so-called blank sky observations. And here I want to give you a distinction between things. So NICER is the instrument we're using mainly. This is the XMM Newton instrument. This stands for Director's Discretionary Time. It is possible for NASA instruments, and for that matter for instruments run by other countries, to request that there be data taken on an object quickly if something really special is happening. And the circumstance is that, unlike normally, you propose for an observation, your proposal is evaluated by peers of some sort, and then the data is yours for some time. For director's discretionary time, the director of the observatory says, we're going to do this, and then it's available to everyone. So we got this specially for this particular pulsar. But you also always, in astronomy, need to know what happens when you're not looking at anything. And over the 20 years that XMM has been taking observations, there have been roughly 1 million seconds of observations of nothing. Of course, it's not actually nothing. It's just positions in the sky where we don't know that there are any individual X-ray sources. This, therefore, is available to everyone. So this is the type of data we're using. We use sampling codes. I'm not going to elaborate on this unless you wish me to, but the point is that when we do our analysis, we have 12 main parameters. You cannot do a search of a parameter space that extensive by brute force. You have to use more sophisticated methods, and we have put together an approach that uses both a nested sampler called multi-nest to get rough initial estimates, and then we focus most of our time and effort using a Markov chain Monte Carlo code called MC that is parallel tempered for those of you who work with this. I will end with telling you about the quality of our fit to both of the data sets. So first, how we model the hot spots. We give ourselves great flexibility. We can have any number of spots. The spots can have different shapes. They can be circles, they can be ovals. The ovals can be any orientation. And we have tried a variety of things. It turns out for this particular source that all you need are 2 uniform temperature circular spots. You may remember from when I showed you the map of the other pulsar, that doesn't work at all. You need to have spots that are very oval. Not here. At least with the current quality of the data, you don't need oval spots, you don't need temperature gradients, but we stand ready if it is necessary with future data. In our approach, the spots can overlap in any way you want. They don't have to be distinct. So you could have one on top of the other. You could have the cool spot on top of the hot spot. You could have the hot spot on top of the cool spot. One way you could get a crescent shape, like the moon, would be to have a hot spot, but on top of it is a cool spot. It happens, again, this is the way the fit has gone. The best fit is non-overlapping, but we can do this. Once we have a spot configuration that we are testing, along with the radius and mass and so on, we predict the photon's energy spectrum as a function of rotational phase. We fold it through the instrument responses and compare it directly with the data. The point down here is one that I can elaborate on if you wish, but the point is that because we're actually using 2 instruments, we're using NICER, we're using XMM, there's the question of how they are calibrated relative to each other, which is something that we've examined and we have a good solution. So that you're not completely bored by my talking, this is a very short video, or animation rather, of the spots. So here we have a wireframe diagram of the neutron star. You'll notice that you can actually see both rotational poles. And that is because this is a very compact object. And as a result, the gravity can bend light. So you can see more than half of the star. The spot you're seeing is one of the 2 spots. This is its location in one of our fits. And this is also the correct relative size. And as we rotate around, we see the other one coming in and then back to the first. So for this particular fit, they're slightly different sizes. However, they are on opposite sides of the star. It's not a perfect dipole, but it's not very far away from that. And this is very different from the first pulsar that we examined. Now, let me go in some detail to discuss how we get radius information. This is tougher than it is for the previous pulsar. For the previous pulsar, we had such a large number of X-ray photons from the star that we were able to just use all of the properties of the X-rays. We were able to use the waveform, the harmonics in a Fourier sense, and so on. In this case, however, we're not able to do that. The harmonics are weak. We can see pulsations, but we do not have enough information to just use that info. So, and again, I'll be happy to go through this in more detail if you like. The key information that we get from combining all of the X-ray data is the modulated fraction of the waveform. You have some overall average level of emission, and then it goes up and down with rotational phase. So the question is, what is the modulated fraction of that? And we have to measure this against the emission from the star. The problem is that with NICER, you also have a lot of emission from other things. It's on the space station, so you have a lot of space weather issues, for example. But combined, we can get this, and this tells us the ratio of the mass to the radius of the star. So we have the ratio of the mass to the radius, and from radio observations, we have the mass, and so this combined is the radius. So it is a more involved situation than it was for the previous pulsar. But this is something we've worked with extensively, and we feel good about our work. And indeed, what we find is that our model is a good fit to the data. This is the same thing as you saw before, except instead of a gray pattern, this is a vibrant, colorful pattern because we're even doing better than we were with the previous one. Again, the chi-square per degree of freedom is excellent. This is showing against the nicer data, and it also fits the XMM data well, meaning that we have no indication that the model needs an extra component. If we had a terrible fit, we would know something was wrong. Of course, having a good fit does not guarantee that we're using the right model, but it is something that gives us extra confidence. Ultimately, what we want to do is to figure out information about the equation of state. Again, this is the pressure versus the density. And this is just kind of a quick look about what we have done. And this is something, again, I'll be happy to discuss in more detail if you like. But essentially, what we've taken is our initial or our prior knowledge of the equation of state is very poor at the high densities involved in neutron stars. So initially, if we were to try to show pressure versus the density, it's hugely broader than what we end up after we've done all of our analysis. We have tried 3 different models of the equation of state. We don't know what those are. These have parameters in them, and we can see that around, so this is log 10, around maybe 2 to 3 times the density of an atomic nucleus, we are really tightening down onto the properties of this matter. This is not just from our recent measurement. It's also not just from the 2 nicer pulsars. It also involves gravitational wave measurements, the existence of other high-mass neutron stars, and some nuclear physics. Another way of putting this is that we can think about what we now understand with respect to the mass and the radius. The mass as a function of radius, the radius as a function of mass. So here what I'm showing, where in each case the blue band at a given mass shows the 25 to 75% level for the radius, and the outer pink region is 5th to 95th percentile. We start with our priors, where it's very, very broad. We add the information we had before NICER. This includes gravitational wave information. Bottom left, we add our first pulsar from NICER, and the bottom right, we have our second pulsar from NICER. And what we end up with is that with all these models, we have this pretty remarkable plus minus 5% range for the radius. And that's quite impressive. But I want to give this to you in a way that is maybe a little more human-friendly, more of a human scale. This is a satellite of Washington, D.C.
Excuse me, Professor. We have a question from Elielson in YouTube. Can I make it now? Or?
Yes, please. Go ahead.
Okay. So Elielson asks, are there any differences in the mass and the radius distribution for neutron stars in binary or single systems? I mean, in your models, you are assuming they are single, or there would be differences?
Oh, I see. Yes, it's a good question. So actually, let me answer 2 aspects of that. In our analysis, we are, when we take our radius measurement and the other measurements I'm discussing, we are in fact thinking about stars as if they were single. Now, if you have a companion to the neutron star, normally this is much farther away, so far away that it cannot affect the structure. And our assumption is that this is a single star is valid to the degree we need it to be. When it comes to the gravitational wave measurements, 4 years ago, there was a double neutron star merger that was seen, and that was certainly coming together and producing a merger and a lot of activity. But the component we are using is basically when they're somewhat separated, how their gravitational tidal fields can distort each other. So that's something you can also, as it turns out, phrase in terms of a single star. Now, in terms of mass distributions, it turns out that if you have neutron stars that are in binary systems with a companion that at least at one time was an ordinary star, so meaning that it was like it's a white dwarf now, these tend to have higher masses than other types of neutron stars, probably because matter has flowed onto the neutron star from the companion. So thank you for the question. May I?
Thanks.
Okay. So I want to put this in more of a human scale. This is Washington, D.C. For those of you who may have visited, you may notice the evil Capitol Beltway, which, although it's not as bad now, during rush hour, it is very bad traffic. Of course, you can also experience that in Sao Paulo, but here this is something people curse at because they have to go into work that way. The inner circle shows -1 sigma for the radius for kind of a typical 1.4 solar mass neutron star. The outer circle, +1 standard deviation. The sequence you'll see goes from the theoretical prior that I showed earlier to what happens when we add information before NICER, then adding the first NICER pulsar, then adding the second NICER pulsar. So starting out, we're very fat. And as we add the information first pre-NICER, obviously it shrinks a lot. Adding the first NICER pulsar, and then especially adding the second NICER pulsar. And this is pretty remarkable. What it means is that we're measuring something which is the size of a city at a distance of several thousand light years. And not only that, but we're doing that to the precision of the size of the campus of USP. That's pretty impressive. And this is not just the NICER measurements. This is something that comes together from many different realms. I believe I'm a little bit over time, and therefore I will simply leave my conclusions up here, and I will be very happy to have further discussion. Muito obrigado.
Thanks a lot for a very clear talk, very understandable. And now let's open for questions and discussion. Please, everyone, feel free. We have already one question. Maria, please go ahead.
Yes, thank you very much, Professor, for your talk. It's the precision that you have is really amazing. I was wondering if you you assume at some point a spherical shape of the stars, and if you would expect some deviation from this.
Indeed. And let me, in fact, show this. As I said, yeah. I have a lot of good backup slides.
Great.
So we are tracing photons from the star to the observer. If then a lot of great simplifications. For example, we're tracing these photons. The photon would travel in a plane and so on. And in fact, when there's rotation, as you say, this is not true. You have frame dragging of space-time, and also the star becomes oblate. And indeed, when we do our work, our ray tracing, which is fundamentally how we go from an assumed mass, radius, spot, location, and so on, to comparing with the data, we do not assume that the star is spherical. There is a wonderful approach developed by Professor Sharon Morsink of the University of Alberta in Canada, something called oblate Schwarzschild. And when you apply this, which all of us have done, you get tremendous agreement. My apologies, these are somewhat small, but presumably you can lean toward your screen if you wish to see them. What we're looking at here is an example waveform with particular combinations, 200 hertz, we have the possibility of doing it exactly right, or numerically exactly, all the effects on the space-time, all the effects on the star, and that's this solid line. We have something, an approximation that actually I introduced with my colleague Fred Lamb, where you assume the star is spherical, but you do the special relativity of the motion correctly, and then you have doing the special relativity correctly and an oblate star, but the exterior space-time you treat as spherical and therefore Schwarzschild. And these are all looking pretty good, but what you can see, this is a fractional difference in percent compared to the correct numerical value. Yeah. And this is our previous spherical approximation. Down here is what you get when you are using this oblate Schwarzschild. Notice that the difference is only a couple tenths of a percent.
Yes.
This is tremendous. It is even much better than we actually need for our work. The other thing you might have been wondering about is when we are comparing equation of state predictions with our measurement, maybe there's a worry that the star bulging out may affect things a bit. However, at a few hundred hertz, here are the differences between the, again, gravitational mass and the equatorial radius as a function of the rotation rate. And you can see that even at a couple of hundred hertz, there's very, very little difference between the two. But I think your question is an excellent one. It's one we have worried about, and luckily it's not a concern.
Great. Yeah. It's really awesome. Thanks. I have another question. Can I do another question?
Sure.
It's completely different. It's related to the energies, the comparison of the energies that observes XMM and NICER. They are the same bands? They use the same bands?
They overlap almost entirely. XMM has reliable energy information down to about 0.2 keV. For NICER, we're willing to go down to about 0.3 keV, and both of them go up to high enough energies that the thermal X-ray emission, which we're measuring, has completely died out. So they have a very good overlap, yes.
Okay. Okay, thank you.
De nada.
Now it's Juan.
Hello. Thank you. Thank you very much for your talk. Can you hear me?
I can, yeah, thank you. Okay,
I have basically two questions. The first one is related to, well, at the beginning of your talk, you give some motivations for studying neutron stars in the sense that you can attain or you can study extreme conditions that cannot be achievable in Earth, in laboratory, right?
Yeah.
So my question is, can you give an example of the physics that you can study in neutron stars that are highly sensitive to the accuracy that you're obtaining in your measurement of mass and radius?
I can, and so that we can look at it, why don't we go for this again? This was a wonderful slide produced by Dani Paz at UNAM in Mexico City. I like the colorfulness. In terms of physics that we are learning, it is, at least the study I'm performing, this is something where we're learning about the nature of the interior of the star. And let me give you an example of this. Let's suppose that we have a neutron star of a given mass, and it's actually quite small. One of the things this tells us is that it is easy to compress that matter. Now, that by itself does not tell us what the matter is, but it does mean that it makes it more likely that you have some exotic components. Exotic components would be things like hyperons, where hyperons are 3-quark bags, so baryons that have at least one strange quark. So by measuring the radius, we can say it is more or less likely that models that involve a lot of hyperons describe the center of a neutron star. There are other things in principle where we might learn not just by the measurements we're doing, but by measurements, for example, of the temperature of a neutron star as a function of its age and mass, that could give us additional info. But the properties of the core leading, in some sense, to understanding the composition, I think, is the main focus here.
Okay, thank you. Well, the other question is related to, I understand that you can constrain the radius mass relation with your measurements, if I am not, if I correctly understood. And is this relation important, or does this relation has impact in interpretation of gravitational wave signals?
Indeed, it does. In fact, let's again go to this just so we have a more straightforward thing to examine. Because you're asking about gravitational waves, you probably have investigated this to a significant degree. And one of the things you know is that when two neutron stars spiral toward each other, as they come closer, they do tidally deform each other by their mutual gravity. The larger the star is, the greater the amount that the star will be deformed by a given gravitational tidal field. And that says that if we are, as we are, if we're measuring relatively large radii, this gives extra hope that we will be able, with additional future gravitational wave observations, to see definite evidence of a tidal deformability. The other thing is, as you know, when the two neutron stars merged in 2017, one of the things that we saw was just an amazing fireworks show in optical, X-ray, gamma ray, infrared, everything. The larger the star is, the more matter that can come out, and the more you would be likely to be able to see that kind of electromagnetic counterpart. So it is quite important for gravitational wave studies.
Thank you very much.
Donata?
Now, Betty, please go ahead.
Oh, hi. Thanks a lot for the very interesting and insightful talk. And if I may, I have two questions. Can I make them in a row, or?
Yes, please. That has been the standard that has been set. So yes, please ask both of your questions.
Okay. So the first one relies on magnetic field potential constraints that you can get out of the observations based on the asymmetries of the rotation and spots. This is one question. And in the same line of reasoning for this question, why is that the second object that you described, you could consider spherical spots? So this is the first question. The second one regards.
Let me answer that, and then you are next in line for your question, just so I can make sure to get this one and that I don't forget some of the details.
Oh, okay, great.
So, and it's yeah, sorry, I wasn't quite sure of what you had meant. So here, this is the weird one. So here we have spots that, based on our analysis, are all in the same rotational hemisphere, and this can tell us something about the magnetic field. For one thing, the magnetic field cannot be a simple centered dipole.
Exactly.
If there are three spots, then it's probable that what's really going on is that, say, maybe this, which we're modeling as an arc, is maybe a couple of regions. So this seems to tell you pretty clearly that there are multipolar components, not just dipole, but quadrupole. And there are people working within our team who have actually tried to model this, and they have been successful. There are reasonable magnetic field configurations that involve a quadrupole as well that can, in fact, give us configurations like this. Now, I think as part of that, you also wanted to know how we can, in some sense, get away with modeling with two circular spots. Was that part of your question as well?
Yes. Why is that? Yes. In the case of the second, you could neglect asymmetry effects, oval spots, and go to the circular assumption.
So it's massive pulsar. Okay.
For the massive pulsar, indeed, yes. I don't have it labeled here, but this is the massive pulsar.
Exactly.
This is an excellent question. It is another one that we have thought about a great deal. And there are basically two answers to this. The first answer is that, remember that this heavy pulsar has a very low flux, only about 1/20th of the previous one. So we just don't have enough data to demand a more complicated spot pattern. But the second one is something that is often not very well understood. As you can see, this is a really small spot, and the other one is small too. You can barely see the other one here. This is a really small spot. Now, why is that important? The radiation coming off of the surface, this is thermal radiation, so it's not strongly beamed. It comes out in a broad region. And what that means is that it smears out details of small spots. If it's a large spot, those details can persist. But this could be a group of small spots that add up to this area and are in this basic region. And it would give us almost exactly the same prediction of the spectrum as a function of rotational phase. So the fact that it's broadly spread out and small means that you don't need extra info. Your second question now.
Okay, thanks. And I'm going to pose my second question because, but I still have some more questions regarding magnetic fields. But anyways, I will go for my second one because the other people will want to ask questions as well. So okay. My second question regards the equation of state. You know, you ended up with for the two objects which seem to be very different, but at the end you got a sample of a potential equation of states for each object, and they are quite similar, in fact. So, and I was expecting for something, you know, really weird or different with regard to this heavier object. Yes, this is this slide. So can you comment a little bit more on this? I see that the threshold is a little bit different, but I was expecting something more, you know, more obvious and more constraining from these equation of states, because after all, these are, you know, these kind of diagrams are very important to constrain these equation of states and the other way around, radio versus mass. So can you comment a little bit more on this?
Yes. So first I want to clarify what I am showing here. This is for different general frameworks for the equation of state. This is what we find as the 5th percentile to 95th percentile range of pressure at a given density. This incorporates all of the measurements at one time. So this is not showing J0030 or J0740. It's both of them and all of the other measurements at the same time. So this is putting everything together. So we're not saying what we would get for one pulsar versus for another. And indeed, one other thing that possibly would help, I think I have this here. So this is a more detailed diagram. These are the different frameworks. Basically, if we focus on one of them, let's say the red one here, you start off with just the prior information you've had, then you add the pre-NICER information, then you add the first NICER pulsar, then you also add the second. So when we get to here, we've put them all together. So I think that may address part of your question, but possibly not. Did I address your question?
Yes, partially. I understand this point, but I would like to ask you your personal views on or impressions with regard to the equation of state, the kind of equation of state that would suit better this new heavier object? Do you have any insight on this?
Well, one thing that I think is even kind of evident with these sorts of constraints is that as you're adding the first NiSAR pulsar and then the second one of the most important aspects of this is that you are increasing the general range of the pressure. So to put it another way, with this new heavy pulsar, the measurement of the relatively large radius, and I did not go into it, but there is a pretty strong lower limit on the radius. That measurement tells you you cannot have a soft equation of state that is easily compressible. So this has implications that some nuclear physicists have discussed. One of the things they've talked about is that it simply means that at a lower density than many people had believed, the equation of state becomes fairly repulsive, so that it's really holding up against gravity. Most people had believed that you would have had to go to higher densities for that to happen, and so they would have predicted a lower pressure here. So I think that's an interesting point of view. As far as what this means for the composition, it seems to be not yet at a stage where everyone can agree. I think the nuclear physicists will always go with what they know and claim that it fits the data perfectly.
Right. Okay. Thank you so much. My other question was in relation to the magnetic fields, and the dynamo process. But we can leave this for later on. Thanks a lot for the very interesting talk. Amazing one. Thanks.
Janata, you were very kind.
I have two questions from YouTube. The first one from Jorge Rueda. His question is, it seems in the model, the model you showed, the photons from the spots travel to the observer without interacting with the matter or electromagnetic fields or other photons in the magnetosphere. Do you expect this to happen and to change the results from the models?
Yes.
Some kind of interaction.
Okay, this is an important clarification. The stars that are being studied with NiSAR are not accreting, so they are not taking matter from a companion. And that is important largely because of that point that was raised. If they were, you would worry a lot about the photons interacting with other matter or other photons on the way out. But these are very low luminosity, and they do not have matter actively accreting, and therefore, once they have left the surface, it is expected that they will travel without running into anything significant along the way. It is very, very optically thin. However, they also have to travel through the interstellar medium. One of the fit parameters that we use is the neutral hydrogen column density. It's basically the amount of stuff that it has to travel through. This is a fit parameter, and for both of these, we have information about that. It tends to remove the X-rays at the lowest energies because the opacity at lower energies is much greater than at higher energies in the X-rays. But we do include that in our fits.
Thanks. Does this fitting these assumptions about the column density in the ISM introduce some significant uncertainty to the results?
The fits that we're using, the column density is a parameter, so we do the best, whatever the best value is our fit. For these two neutron stars, this does not appear to be a limiting factor. The information we get is not being destroyed significantly by the interstellar medium.
Perfect. Thanks. And now the question from Nathan Valentin. He asks, can we measure the changes of the spots, and how are their evolution how would be the evolution?
Yeah, another critical question that we worried about a lot. I can tell you that for these two pulsars, for the first one, we accumulated about 1.9 million seconds of NICER time, and for the second, about 1.6 million NICER seconds on the source. And these are accumulated over roughly 2 years. So we're accumulating this, and we're putting every photon in its rotational phase bin, and therefore we're just adding it up. And therefore, the question you're asking is a pretty important one. In particular, what if those spots are moving? What if their size is changing? What if the temperature is changing? In that case, the kind of stacking analysis that we're doing is not valid. Because this worried us, what we have done for both pulsars is we have taken different segments of the data. The first half, the second half, the first third, the second third, the third third. And we can directly compare the rotational phase-dependent spectra for each of these segments to determine whether they are consistent with being the same or whether there's evidence that they are very different. If it had turned out that these are very different, we would have had to use different analysis techniques than what we're using. But in fact, these are completely consistent with being the same. And from a theoretical standpoint, this is reasonable. These hot spots are not being caused by matter falling onto the surface from some distance. This is because these are radio pulsars, and the magnetic fields in these neutron stars can accelerate electrons and positrons to high Lorentz factors, and they slam into the surface. But that configuration is not something expected to change over a human lifetime. And we have confirmed that there is no apparent change. So that's our working assumption, which seems to be reasonable based on the data.
Okay.
Perfect. Thanks a lot. Now, Herman, please. You can go ahead.
Thanks for the talk. My question is about the measurement that has been made by the other group of NICER.
Mm-hmm.
As far as I know, the result is something like 12 plus minus 1 kilometer. So I understand that there is an overlap with the measurement of your group, but there are also some differences, and I would like to know your comments about this. Well, I have other questions, but I can make this after.
Indeed. As you say, and this is, I think, the headline I'm going to have, it turns out that the -1 standard deviation radius is especially important. And just as you indicated, the group, which is led by Tom Riley, found a value of 11.4 kilometers. We found a value of 12.2 kilometers. And because this is quite a significant difference, even though there is overlap, the team had spent a lot of time thinking about analysis differences. The most important difference has to do with the footnote that I skimmed over early in the talk, remembering that we are using two different satellites, NICER and XMM. And one of the big questions you ask is about their cross-calibration. And by cross-calibration, we mean that if you have some flux that it is being registered, you have to know how the instrument is working, how efficient the instrument is in seeing photons. This is a classic problem in X-ray astronomy. But there has been a lot of study, and what people have found is that when you look at NICER versus XMM, in the energy range of interest to us, there is less than a 4% difference. That's a very small difference. We assumed that it was known very well, and when we did our analysis, even allowing the difference to be as much as 10%, we found no significant change in our answer. The Riley et al. Team has elected instead to use a much broader difference. they allow the difference to be 50%. And they have, however, done an analysis in which they say, well, what happens if we use the normal calibration, so something closer to what's actually being measured? And as you can see, they go from 11.4 to 11.75. This is almost half the difference. You also have, they imposed from the beginning that the radius cannot be more than 16 kilometers. As I indicated, our approach is to allow any radius that fits to be included, but if we imposed this prior, we have very slightly changed our radius. So basically, the unaccounted for difference is not 0.8, but 0.3 kilometers. The rest of the difference is probably due to statistical sampling and how the different ways in which we treat the blank sky background. But thanks for the question. This is something that obviously has worried us. The main thing, though, is that the cross-calibration, they're using something that's extremely broad. We're using something closer to what's measured.
Okay. My other question is concerning the equations of state, you assume. Can you show the slide where you show the equations of state?
Yes. Do you mean the one with the final result or the one with the
one with the priors?
The one with the priors, yes. Okay. So this is, let's see, here we go. So this one?
Yes. My question is, to what extent does this include exotic possibilities, like, for example, transitions to quark matter with very high density shunts? So, in a sense that you can go very to the right, just with making a shunt transition to quark matter, or even more exotic possibilities, just such as strange quark matter, where the low pressure regime of the equation of state is not present, like in a hadronic equation of state, for example, and how this would impact your results.
Indeed. And this is one of the reasons that we actually used 3 different frameworks for our equation of state, because we wanted to explore that. The old workhorse of these things is the piecewise polytrope. So this is a log versus log, and it essentially says that for a given equation of state, you can have something that obeys one power law and then another. This one can have phase transitions. We are not looking into particular microscopic composition. We are parameterizing the pressure versus the energy density, but this is something that absolutely can accommodate phase transitions into whatever. The spectral equation of state, the one to the top right, this is the one that is used by the LIGO and Virgo teams. This one cannot allow there to be phase transitions of that type. This Gaussian process thing can. So within our set of equations of state, we do have ones that could allow quite sharp transitions into different types of matter, if it can, given that that is typically going to give you a relatively constant pressure over some range of densities.
And concerning the other possibility where you have strange quark matter in the classic way, where you have these stars that have a density continuity at the surface of the star in contact with zero pressure, what will be the situation?
Yeah, so that's of course an interesting example of the bare strange star. There are some aspects of neutron stars which would barely be affected by that. An example would be tidal deformability, because almost the entire aspect of tidal deformability is going to be at below the densities where you can have that. So basically, if you ask where can the density discontinuity be, the matter you would leave out at the lower densities contributes almost nothing to the tidal deformability. However, the radius is a different story, because if, for example, you have that matter to, let's say, nuclear saturation density, you could be missing 1 kilometer off the surface. So what I would say about that is that if those are the types of constraints you're thinking about, the types of equations of state, then the predicted radius would be even lower than what we're looking at here. So the predicted radius would, if with a crust you'd expect 12 kilometers, without the crust maybe you expect 11. So it would tend to make it tougher to match these results. The high radius is not as easy to accommodate in those ways.
But Cole, let me add that there's a loophole there, because in self-bound models, the highest the mass, the highest the radius. Therefore, when you query about 2 versus 1.4 or something solar masses, it indicates, the theory indicates that the most extended one will be the more massive one, not the other way around. So therefore, what you're obtaining is something like a very sharp, a very steep diagram in which the radius goes all the way up from the scale of 1.5 to 2 or something. This is not unlikely for strange matter. Rather, if you refine your measurements, and it happens that the lowest mass is actually smaller than the other ones, it will indicate that you can easily comply with your data without any crust, which is, of course, the deformability of the other constraints also apply, but they are easy to fulfill up to now. Actually, we have a paper that was coming out this week or so, showing that there are no real constraints, not really strong ones, when you take all the whole data inside. The real thing is that you have another behavior, but different behavior from the conventional matter, but it does not, it has nothing odd enough to be at odds with the data. So that's even without crust or without the truth, that is maybe not the whole story. That's my point.
Okay, so the radii we're getting here are actually fairly similar.
Yes.
And it's not that the one that is 50% more massive is much,
Yeah.
But the other point I want to make here is, if we're talking about a genuinely bare strange star, then one of the assumptions that we're making in our full analysis is not valid. We are, in our ray tracing and our analysis, we are making the assumption that you have a hydrogen atmosphere.
Yeah, okay. Yeah, that's true.
And that's also something which has been at least a bit of a challenge. I know people have found ways around it to explain things like thermonuclear X-ray bursts with genuinely bare strange stars. However, if you have something that is a strange star self-bound with even a relatively small additional component of normal matter, then both of those assumptions work fine. So I think a truly bare strange star needs close examination, but adding, even 10 meters of matter on top is something that allows you to get around some of those other constraints.
Okay, I agree with you.
Thank you.
So I had a question, if Reynaldo lets me, that is related to this one in a way. You know that up to now, the most accurately measured low masses for neutron stars are around 1.17 solar mass. This is likely that this says something about the minimum neutron star form in nature. Okay, so it may be around 1.1 or so. Is it possible to take a measurement much in the same way that you did for the heaviest one, to these a couple of examples that feature a very, very low mass? Unfortunately, there are no 0.5 solar masses there, because that in that say the difference would have to be enormous, and they will answer at once the question of the composition. At least have a very good idea of that. But are you planning to, or is anybody taking a look at that low mass objects of 1.17? Even though if you believe in that progressive determination of the neutron star, you should obtain something which is not very different indeed. Okay?
The answer, unfortunately, is that there are no neutron stars of that mass that are bright enough in X-rays.
Okay. So that's they have a couple of examples, and they have been claims for other objects that were outrageous, doing the fit of the black body and so on, that were, you know, but this cannot be confirmed. I mean the masses may be high or medium size after all, and not necessarily below 1 solar mass or so. But
Right.
so you have a list of forthcoming objects, right? So there's the idea of extending this. So you have a few more candidates, right?
We have one. So our team actually has an answer to a third pulsar.
Okay, fine.
Good fit. We have a radius.
So you're working on the analysis.
And this is something that an important approach in the NICER team is that both teams need to be able to get an answer and compare. And the hope is that we're going to be able to publish that later this year. I would like to see that. As far as the others, there are others that are being seen, another high mass one, for example, but even though one of the great features of the NICER observation schedule is that people are willing to stare at neutron stars for more than 1 million seconds. Even with that, some of these are just too faint.
Okay, thank you very much.
So, if Professor Coleman has some minutes available after we finish the broadcast, so we can continue talking informally. I think some people have some things more to discuss. If you have available. And before we close the transmission, is there some interesting question that appeared here from someone who was following your seminar? If you could answer, is the person identifies himself by 7 true in YouTube, and he asks, he or she, is it possible to a planet to have life in the neutron star's orbits, or the radiation would be too high?
This, of course, is a fun question in many ways, one of which is, as you know, the very first exoplanets were discovered around a neutron star. Now, in that particular case, that neutron star has a total luminosity from spin down, which is about 5 times larger than that of the sun, and these are planets that are relatively close. The question is, could you have life? I think that it would be a challenge to have life on the surface. However, if you have planets like those, where 2 of the planets are 3 or 4 times the mass of the Earth, going down in soil, going down in water, if it's possible to have that, I think you would be shielded from the radiation. And you do have a lot of energy, which could be used for life. For me, although of course I'm an astronomer, one of the most amazing things I've heard about in my life relates to biology, extremophiles. You have microbes, single-celled things that can live in extreme heat, cold, acid, basic environments, radiation, vacuum. So I think that with energy and with some protection, I don't see any reason why microbes could not exist in planets around a neutron star. I would be a little more suspicious of claims of advanced life. I think we advanced life creatures are much more fragile.
Thanks a lot, Professor. I would like to thank you again for being here and sharing your research, your knowledge. And also would like to thank everyone participating in the seminar, contributing, also with questions. So thank you again. We will stop the broadcast in YouTube now, and we can continue talking informally if you have some minutes available.
I do.
Bye, Cole.
Thank you.
Bye-bye.